Mayan, can you do that in Google AI Studio, or what setup are you using to do that? Oh, OBS. Okay.
I'm sorry, what's OBS? What does it stand for? Oh, okay. Wait. So you have a recording software on your machine. You configure it to record. You could turn it on for a particular window, right? Is that right? Not for the whole operating system and everything you're doing, but for that particular window, like sharing to Zoom or something. And then it'll take pictures of all that, and then afterwards it stops. You stop it, and then you have all those slides, and you do, and so you can analyze them. But so why would you do that rather than just recording? Just because you don't have to record, and no one has to know you're doing it, or video? I mean, why not just do a video? Oh, yeah. So it's rewind. You're doing your own custom version of rewind, and then what? And do you actually do that? And so then when you kind of do it, how do you tell me how it's helped you out? You know, so it's like an extended memory that you can, but how do you literally use it? You query on it, or what do you do? So yeah, it's recorded you for the last hour, and you're like, shit, I forgot what I did at the beginning of the hour. I want to look back at that. Maybe it was yesterday, an hour yesterday. I want to look back at that hour I recorded yesterday. What do you do, literally?
So do you think with all these new features, we're going into fantasy land, where everything is a fantasy, and you never know what's true, and there's no verification, no validation, no. It's just like this is a totally different universe of how to live.
On that point, somebody who builds this and all that, caveat emptor.
Yeah,
You
yeah.
know, all it says is when you think about it, I mean, this stuff, even when you go back 25 years, this stuff is kind of new. So anything you see that's digital, was it ever really real? Shut off your computer, go out for a walk.
Yeah, exactly.
It's okay for anything digital, anything on the internet to be entirely fabricated and generated.
Well, I mean, I just had a recent episode of that myself. I was gonna anyway. I don't want to. I can talk about it after he finishes this.
Mike, actually, if you go to Simon Willison's blog, he has a good example of how it generated I don't know, a poster-like thing from, he has this tool called a Dataset SC, and he asked it to generate a poster of what the tool does, and it really did very good job. I mean, the reason I bring that up is I'm not going to be doing orthographic projection or whatever anytime soon, but that the example he used seemed very apt. Sure, just a sec, let me put that. And he has that example. The reason I bring it up is, for example, following along, Alan can probably generate a one-pager on his tool on verification and have people kind of visually understand what's happening. Actually, more than that, this isn't the first one that I'm talking about up at the top, like where he has the tool, the dataset tool, and the poster that it created for it. You had it initially, and now it's gone. So I don't know what's going on, because I have still it's a post on November 20th, 2025. Sorry, let me see what you have on yours. Yeah, that's the one. Yep. So that, like, to me, that gives a really good example of kind of infographic explaining how the dataset open source project works, right? And it really gives you the flow of the tool with various components to it and stuff. And something like this is practically very useful, like to understand or to explain to somebody even something that you have developed, and quickly, so that people can grasp something really quick. Like, what does dataset do? And it has given you image which conveys all the different components of it and so on. So I thought that was a good practical example of what many people were not playing actually in the image space, but can still utilize it to explain things that they have done to others. Yeah. And the details, right? Like the dataset application core, it kind of points out the layers and the ecosystem, color codes it appropriately. So all of that is really kind of impressive.
for detection and tracking. The detection. Hi, I'm Christoph and I'm a research scientist at Meta. The SAM-free model can now segment all objects with just one concept prompt that can be short text phrases or visual examples. The model has two separate transformers for detection and tracking. The detection task works on an image level or frame based in videos, and it just outputs all object instances on a single image for the specific prompt. And the tracking task has the task of following each individual object throughout the video, and they're coupled together to perform the final task. So when we did this research, we had a certain challenge that we faced. Tracking and detection are fundamentally quite different. For the detection component, the model needs to learn similar or the same representation for different object instances. So if you have one dog and another dog, you need to learn the same dog representation for each dog. However, if you perform tracking in a video, you need to learn different representations for each instance, even if it's the same object category. So one dog needs to have a different representation than another dog, than another dog. So we really leaned into prior research by Meta to build SAM-free. We used the SAM2 model for the tracking component. We used the detection transformer, which was released by Meta, as a base for the detection architecture. And we also use Llama in our data engine as an AI annotation tool. So there are many applications for SAM-free. It can be used as a standalone tool. It can be used, for example, in a multimodal large language model. Or in the Instagram Edits app, you can use SAM-free to segment people, objects, and then put fun effects on top of these segmentations. We believe SAM-free will be an important milestone in the AI field and hope that the research community keeps building innovative solutions on top of it.
Selection to find others.
Hi, I'm Christoph and I'm a research scientist at Meta. The SAM-free
While Mayank is sharing, I'll say something a little controversial, perhaps. I've always thought that the meta models generally tend to be more consumer-oriented versus performant for enterprise use cases, like real valuable stuff, building stuff. And surprised to see Citadel, which is one of the largest hedge funds, they've pretty much funneled a large portion of their technology investments into Meta. Now, this is a fund, and I know people who work at Citadel and certainly trust their ability to understand global markets and sort of being able to predict the future. Without going into any further details, the fact that Citadel is going so deep into Meta in their investment portfolio is, to me, certainly worth understanding a little better. Is Citadel Meta just Citadel Meta?
Well, do you think that has anything to do with them giving $100 million to each worker?
Citadel?
They had that hiring phase where they gave $100 million to people to come work for them, and so I would think that would tend to look good to investors, right?
Well, the reality, as far as I understand, is it was only for a few people, and those people who were at Meta, a lot of them got pissed off and quit.
I could believe that.
The few that got it, it's one of those things like money really talks. And it's we're talking about humans here. If I see my coworker make more money for doing the same work, I'm gonna be pissed. And if I'm the manager and I'm publicly going to pay someone differently, it could be, I should expect the team to they'll talk and they'll know and they'll see it and they'll come up with completely incorrect reasons of why I did that. And, it could be, there'll be stories about, well, it was gender, it was whatever,
I mean, it definitely changes the culture,
It
correct?
changes the culture, and it's
Yeah.
not something that you want to try to have. If you
Well,
look
obviously they did want to try to have it because they did it. So, and I don't think they're dumb or anything. I mean, it's
no,
like, so they wanted to change their culture because they were my gross version of it is they wanted to change their culture because they were losing and they didn't want to lose. And
there's
so that's
that. And then there's having, Meta was a consulting client of mine on their Oculus supply chain side, trying to come up with innovations on procurement and so on. Meta as a corporation, besides their individual properties, WhatsApp and all that, Meta leadership index is more on the younger side, not quite as business savvy as you would expect, despite the amount of money that the higher salaries that you can probably get if you get a job there. And at the same time, they go through these massive rounds of rifts and so on that seems pretty arbitrary and random to people who work there. That and you've got, and that this is one of those companies that have forced rankings. And so from an HR perspective, organizations that have forced rankings, when it really comes out, you better treat them really, really high. McKinsey is one of those companies where it's never a question of whether you're going to leave. It's a question of when you're going to leave. They help you leave so that
yeah. Going back to your original thing, which is why, Citadel invested.
Mm-hmm.
So why do you think Citadel invested so much money? I mean, there could be a couple of reasons, but what do you think?
The core part of their investment, in order, the due diligence would be show us open kimono, what it is you're building and what your pathway to going to market and growth would be. And that's where someone it would have to be, for this kind of investment, this would be Zuckerberg himself, who would be making that pitch to Citadel to say, here's what I want to do. You can,
right.
Here's what I'm going to put down on paper and a commitment to you that if you make this investment or you guys take this kind of stake, here's what I am going to do. And that is convincing enough what the long-term play is. And long-term in this space is going to be about 3 years. So over the next 3 years, what are they going to do? If they're going to be infusing it or there's a pathway. At this point, even when you look at OpenAI, it's coming down to simple old search engine optimization. OpenAI, ChatGPT is going to get littered with new next generation ads, stuff pitched. And so Meta makes a tremendous amount of money from advertising. It's Meta and Google. They pretty much dominate. And so I think they may have figured out some way to be able to infuse it into AI better than anybody else. And so Citadel is saying, we definitely see you doubling 2-3x your current stock price. So we're going to make a bet. That's my
and also the number of players that Citadel can impact is limited. So the number of big players, right, is limited. So you have it makes sense. I mean, I don't know if it makes sense, but I'm not surprised.
Yeah, I wonder how much of it is also another factor influencing maybe their decision is the fact that Meta's models are open source. And, there is this drive in open source world to become competitive with the closed products. And that does tend to also lead to other people building on top of yours more easily than the closed stuff. So I don't know.
I
how
don't know.
much-
I mean, my cut on the open source things is this stuff is getting so complicated. I mean, so you're open source. So it's going to take you 3 years to understand that. And, you know, you already got the Chinese, they got their own versions of versions of stuff. So even if I know something's open source, it doesn't mean that I'm going to like, I'm giving everything away. It just means that I'm potentially getting more researchers who understand it and I can hire them and they understand my stuff, maybe, but I don't even
No,
know about that.
I'm thinking of it more from the user standpoint, that there are more people who want to build it because they can customize it and they're not like bound to some other company's whims.
Yeah,
and
yeah, I understand.
stuff. That's the angle that I'm thinking of, which is a lot of people don't want to get tied into one product or one pathway for progress and run the risk of or reveal their information to a closed environment.
I think
Yeah.
Srinivas makes a really good point, if I may. I can share my screen on a particular slide, a presentation I gave, and this is an old slide of mine. Many of you might have already seen it. Mike, may I take the screen? Okay. So I think Srinivas is absolutely correct. The model at the center of orchestration and enablement, and of course, data, all of that 100% matters. So the model right at the middle, at the center, does not matter. And the reality today is the Chinese more than proven that they can develop better models, despite the massive constraints that they have in terms of GPU access and so on, they are able to build better models simply based on the fact that they've got better math going into the models. If you look at the DeepSeek architecture from a year ago, I did some presentations on this, like how and how they're doing this, and so on, a couple of years ago. They're at pretty much at parity with the US closed models, with the exception of Google Gemini 3, which right now is, the metrics are off the chart. So let's keep Google out of the picture. If you look at Meta's Llama, if you look at OpenAI and so on, compared to the several different key models coming out of China, they're brilliant. They're completely ahead. And where rubber hits the road, Azure uses DeepSeek. They took that open source model, they've refined it, and it is infused into most of Microsoft's products. They may have done a massive deal with OpenAI, and they'll resell OpenAI, the models which a lot of enterprise companies use. MoveWorks uses the latest OpenAI models, and you name it, they all do. But for a lot of things, by default, if you don't specifically pick OpenAI on Azure, it's going to default to those open source Chinese models because they are so performant, and they run better, et cetera, et cetera. So I can go deeper into the same point, but I think that's really the core takeaway. The models don't matter, and it's really about orchestration and enablement and infusing these technologies into your business workflows, and at the same, and just transforming your organizations from the ground up. I'll shut up now and get off the soapbox. And open to any feedback, critical or otherwise.
Yeah, that makes sense. I mean, I guess my point was simply that so okay, I guess I'm kind of agreeing with you. I mean, the model is just a part of the whole flow, and whether it's open source or not, at a certain level, it's okay, but it's not as important as you necessarily think, I believe. On the other hand, it's important. I guess the point is, when is open source effective and important? It's important when you can get more people using it, and therefore more variation and things. Although it doesn't necessarily mean that translates into like enterprise applications per se. I mean, if you look at it from that point of view, enterprises usually have enough money to be able to do things on their own, whether it's open source or not. I mean, whether they use, in other words, whether they're using open source or whether they're using proprietary models, from a cost point of view, they don't really care if you have enough money, right? You just use the money. What are you going to use the money for? You know?
Look at this. This is something that's not reported. This is from private personal relationships. Eli Lilly is the first pharma company to hit $1 trillion in valuation today. Their CIO has decided, and that Eli Lilly is not going to go with enterprise frameworks, models, and companies that have already built stuff like Glean and MoveWorks and so on. He doesn't want that. He wants Eli Lilly to build everything natively on their own. Now, that's a extremely bold statement to say, I may be a pharma company. I'm a $1 trillion valued suddenly company because of GLP-1s, because the world is too fat. And I've got a drug that helps them, and I'm making so much money that as an organization, as the chief information officer of this organization, I will have software engineers working full-time or consultants, where I will engineer and build the entire software stack for AI that I own myself completely, so that my company can use it for doing novel research, drug discovery, all of that, and just everything, even internal operations of human resources and IT and supply chain procurement, you name it. I'm going to do it all on my own. As the CIO of this $1 trillion company, I'm going to be an impressively large technology company. That's saying a lot, even in this age of AI amplification.
Yeah, it makes sense. I mean, I can understand the reason. I can understand that reasoning, right? I mean, especially for something like I don't know, a company like that's so big that there's so many usages of AI that it's not just about drug discovery; it's about everything else too.
Correct.
And and this is a fairly new area, really. I mean, I know everybody's all over it really quickly, but year-wise, it's not that long. So it's not impossible to think you can just get in on the ground floor and build something and keep going. I mean, from a certain point of view, I know it seems like everything's condensed and going so fast, but in some ways it's not. In some ways it is. I mean, there's certainly a lot more bodies on this problem than there have been on other problems in history. So that's accelerated it for sure. Anyway, I don't know. I don't really.
Has anyone seen the OpenAI video? So I mean, I think last week I was feel a bit kind of shell shocked by all the Google stuff. But then I felt that's kind of like the advances that all of these companies are probably making, and they're just kind of giving the trimmings of what they're doing internally. So, so with OpenAI, it was essentially what it sounded like in the interview was just like, and I don't know how much of the credibility is, but there's essentially you now pursuing this kind of LLM or AI just with just the existing architecture on solving discovery problems, not even necessarily problems that are like enterprise anymore. That's sort of like the maybe something that's current state, but like the kind of models they're doing are just solving like energy, just like basic scientific discovery problems, which is quite profound, because essentially it's like the next evolution of like LLM, which could actually be very quickly, right? That they might not be usable. They're actually not targeting people who are using LLMs. It will be LLMs using LLMs. So it's like, from that sense, I can kind of see why a lot of these enterprise paradigms is becoming more like a use case where the solution is known and they're all kind of spinning off into like doing different things. Like Google is doing the system engineering, and then all these other companies are kind of, you got picked like a niche with AI, and it's not, it may not be the end user that's the biggest use case in the next one.
Yeah, you just outlined agentic architecture. The word of 2025 was agents in AI.
Yeah.
The word for in 2026, at least for the first half of 2026, is, in my opinion, agentic enablement. Or
Yep. I believe that it's not it's AI. It's AI enabling AI.
Yeah.
and enable AI. So it's kind of like a recursion.
And if you look at any kind of agentic workflow, and so on, I mean, the Google sessions that happened last week were absolutely brilliant, and that they outline, even in their agentic architecture workflow and the design patterns and so on, you've got LLMs underpinning like each and every unique agent with even multiple of them. And then, of course, evaluations, how important that is, that really has the LLM as a judge, all of that. So yeah, you're going to have, and of course, there's this notion of enterprise of, well, what's going to be the control tower for all of these agents that you're going to have, where ultimately, if your IT department is going to be the one managing all this technology, IT will have more, in air quotes, employees with agents, AI agents, than HR has employees. That sounds cute, I recognize, but it isn't a useful point.
Well, yeah, good talk, guys. I gotta go. So I guess I like the SAM3 stuff. I did a project a long time ago that never completed because at the time the technology wasn't there. I don't know if this would help, but maybe not. I was trying to find in trail cam photos where I was trying to find, and they take pictures of bucks and does, deer. So this is for hunting, and they wanted to find the bucks. And so you tried to find the deer with the horns in trail cam photos. And I'm telling you, that was very difficult because the horns in real life, their horns on the animals are very hard to segment because they mix in with the trees and things and the bushes. And yet in the internet, domain, it was very easy. So when you did internet photos, I had very good success. But when I went to real trail cam photos, I had like 20% success. It was and not enough to be. So it's interesting. I'm looking at this SAM3 photos and I'm saying, yeah, there's a lot of internet photos here, and segmentation is a little bit easier on internet photos. Everything's all kind of pre-segmented a little bit. And I know this doesn't make sense to some of you, but they're not like necessarily all real life tracks or photos or things like that. Anyway, that's my comment of SAM3 is it looks very cool, and it may work on the Bucks versus Does problem, but I'm not sure. Yeah, but that's in this particular photo, that's because of the motion. Okay, so that was the other thing about the Bucks versus Does. Trail cams are sort of like slow motion photo videos, and when you have a video and you have something moving, it's much easier to segment it out. So this is, that's impressive. I'm not saying it isn't. I'm just saying that in this particular case, it's the motion that allows you to segment that. I think. I'm just saying that when you apply these techniques, no matter how good they are in the wild versus on internet photos and stuff, there's a different success rate. That's all I'm saying. And I think that's I mean, in retrospect, that's, yes, what do you expect, right? I mean, but segmentation is a huge problem. So I appreciate any improvement. So yeah, it's great. All right. Well, thanks a lot. Now, see you next week.
Thanks, everyone. Have a fantastic week ahead.
out domain. And then the text here on the right is cardboards are technically in the corner of the room. And then you see that you get like 12 tokens. But this is just 10 words actually. And when you move to the right, particularly it says cardiomyopathy causes heart muscles to thicken and pump less efficiently. If you look at how many tokens you get 6 tokens, but particularly because this is a text domain, there's so much tokenization happening in the word cardiomyopathy. And this is quite important because if you want to adapt the language model to like a new domain, what people literally do is just pick the model, do not update to tokenize, and like you just move on. And that, if you leave it that way, you get like too much tokens. You get like some sort of over tokenization. If you also look at this same problem from a multilingual perspective,
Can I ask a
in
question?
previous, yeah, sure.
Not too early. Just to understand, we're trying to understand the basics of the problem. So why is it a problem if a word is now tokenized into 3 or 4 tokens?
Okay, yeah, so it's a problem because, okay, I'm going to talk about some of the problems, but largely 2 problems that we've identified is it costs too much when you get too much tokens because everyone is charging per token. So I wouldn't want to get too much tokens. 2 is that you learn very weak representations from tokens. Ideally, I want to learn when a word is over tokenized into, I think the lowest form of tokenization now would be into individual characters. You start losing meanings because you want to learn words together, and that gives you richer representation than just learning individual characters in the word, and that gives you a poor representation of the sequence in general. So those are the 2 line of work that have really shown that this is the problem, and people have done several research trying to like say, oh yeah, what's happening here? I hope that answers the question though. Yeah. So when you go into the multilingual perspective, so this is a text with English saying, make sure that your hands are relaxed as possible, stay hitting all the notes correctly, and also try to like make much strenuous motion with your fingers. Literally, when you translate this to Japanese, you get like 53 tokens. And when you move to like Fujambi, which is another language, this is exactly the same text. And you get like 254 tokens, which is completely readable. So these are like problems that you see across languages when you move away from English that people really don't talk about.
Crazy that this is more tokens than characters.
Yeah. Yeah, this is like a lot more, which is a very, which is not very.
Yeah, in Chinese and Japanese, each character is always more than 1 token because you can't afford to do character to token mapping because there are just way too many characters, not just 26, right? Thousands.
Yeah. I mean, that could make sense, but if the tokenizer in itself doesn't support like these languages, that becomes a very big problem because again, it falls down to byte, and with byte, you have problems like those.
Yeah, is your the coloring in the Japanese case, you still color each character in 1 color, but it should be like some characters would have more than 1 token, right?
So I think so. This is exactly how you get to when you go to the website.
Yeah, I'm just wondering if there's some error there or something I didn't understand.
No, I maybe the OpenAI guys will have to fix that. I don't know how to speak Japanese, but thank you for pointing that out, actually. So when you look at this across multiple languages, I just shared like 3 languages, so this is a work by someone else. You particularly see that the number of, when you move away from Latin script, the number of average tokens for the same text continues like to skyrocket. And then like if you keep going to Arabic, to Thai, Hebrew, and a couple others, this happens. And then the impact of that is that LLMs charge per token cost, and then this is like the relative cost that the work studied per English. I think this particular work came from when ChatGPT first came out in November 2022, and when they discovered that it costs more to chat in Japanese with ChatGPT compared to like just chatting in English. So these are like other things that makes this unfair, the way we currently do tokenization across languages. That's currently unfair to non-licensed scripted languages. And because of that, we were now saying, how can we build models that can adapt this tokenization to a target domain? And we define a target domain here as language, or maybe a medical domain, like we've seen that you get more domains, you get more tokens when you move to a different domain. And then you still want to capture meaningful context effectively. The major limitation is that BPE produces like too many tokens and over-fragments the checks when you move to a different domain. And that led us to Flexi-Tokens. And Flexi-Tokens particularly, you could see the impact of Flexi-Tokens here. You have the BPE and the Flexi-Token model. Before adaptation, the model state, this is what you get. And then after adaptation, you see that we start getting more semantically meaningful tokens. Like year old is a phrase you use in the medical domain. By the way, we adapted to a medical domain here. Diagnosis starts to become a word, and hypertrophic is also becoming like more word. So that's basically what you have when you move into, this is what we're trying to go, what we're trying to achieve. And with the next couple of slides is now going to talk about how we're able to achieve some of these results and the impact on downstream performance. How we did this was particularly to use a model that allows flexible tokenization. Our goal again is to ensure that when I have a tokenizer that tokenizes to a pattern that's fixed during pre-training and I move into a new domain, the tokenization should also evolve as I move into that domain. And we use the hierarchical byte-level model to get the best tokenization. So this is basically a high level of what's happening. I think some of these might seem familiar to you guys if you follow the whole hate net gist on Twitter. So working through this, you have a multilingual language model. You pass it through a couple of transformer blocks. You have a boundary predictor that does the tokenization for you. You pass it through like the main transformer blocks, like the main language model inside of it. And then the output of that, you kind of do some upsampling, and then you pass that back into a transformer block again and you get an output. So largely this is categorized into the beginning, you do some sort of tokenization. In the middle, you do the normal language modeling. And then afterwards, you decode your output. So that's how you could think about this. To look at this more specifically, this is how some of the how the architecture is designed. So we're using a hierarchical transformer model here. And particularly what happens is inside of the model, you have your set of tokens here on the left, and then you pass it into a couple of transformer layers. And then that representation from there goes into a boundary predictor, which is this. A boundary predictor is something I'm going to talk about. But it could be, for us, we use an MLP as a boundary predictor. So a boundary predictor just predicts ones and zeros for you to say, hey, hi, this is how you tokenize this text. And then you now pull the representations that fall in between a token, that fall within a segment, and then you get some shortened tokens. That you pass that through a couple of like main, now this is actually your language modeling layers. And then, so sorry, the image keeps restarting. But that you pass through your transformer layers after you pull down and then you decode. Let's just wait for a minute or a couple of seconds for this to finish pulling out. And then after you get this, you get your tokens, you upsample back. Upsampling will now be duplication here. You pass through a couple of transformer layers and you get the outputs. You can observe there's a residual connection at the top. So basically, this is the general idea of HNet, kind of hierarchical transformers, basically. I think HNet and Hourglass are all hierarchical transformers. The question will now be, so how do you train this in such a way that you make the tokenization very adaptable? I have a couple of notations that I just picked from our papers. I will try to like describe these based off of previous work, so it becomes easier. But the notations are not very static to our paper. I try and in a couple of slides, I use some visual representation to make it more understandable. So if notations are not very clear, it's fine. we can just look at the visual representations. So really what you want to do is, because your transformer, your model itself has a tokenizer inside of it, you want to have two losses, one to control the tokenizer inside of the model, and the other one to control the actual model itself. So that's going to lead you with two losses, which is the next token prediction loss, and then a boundary predictor loss. And then on the left is the like normal next token prediction loss. On the right here, particularly, which are underlined with red, is just a loss that is a binomial loss where you're trying to tell the model that, hey, yeah, sample X number of tokens from this sequence, sample X number of boundaries from this given sequence. And then if it's too much, you just penalize the model for like not giving you the accurate sample. To make it more specific, I added some notations here. Lambda is just is a weighting factor, but particularly what this work did. So this is not my work. This is the previous work. What they did was to try to say, for a given language, they use different sampling rates for each language. So script here. So what this work was trying to address was that, oh, how do we make tokenization equal? How do we make the number of tokens equal for different languages? And then they did that based on the script level. And for a given script, they use different sampling rates. Lambda is a weighting factor, X is the given script that you're working with, and I particularly, which is here, is a given, it's an indicator function saying this is the script that I'm working with or not. And then binomial is just, hey, yeah, giving n sequence lengths, sample X number of boundaries within the sequence length. Basically, that's what's happening. And then you control these with your beta. And control this with beta and then case number of tokens. I'm going to talk more about like what this look like in practice in subsequent slides. Particularly, what a boundary predictor look like is simply an MLP. You pass in your sequence length into an MLP, and then it predicts ones and zeros if your boundary should fall at that position. So basically, you just you apply a sigmoid function to the output of the MLP, and then you get ones and zeros, and then you sample with that. To make this differentiable, you use a Gumbel sigmax. For us now would be a Gumbel sigmoid function to do that. And this final text here is we use the alpha to control the tokenization rate. So if I give you a sequence of 100 an input with 100 sequence lengths, and I want to tokenize it, and I want to compress it 3 times, that's going to now be 100 divided by 3, which should be around 33.3 number of tokens. So at the end of the day, what I want to do is to compress the sequence. I want to compress the sequence, which is what tokenization does, but with a controlled factor, which is alpha, particularly. So the limitation that we were trying to address with previous work is this is currently inflexible. This doesn't allow tokenization to change when you move into a new domain, because what you're trying to do is like you're trying to tokenize to a particular value, which is alpha, and alpha controls the tokenization rate. And what they also did was to say, oh, given the domain, given the language, for each domain or for each language, use a separate boundary predictor for it. That would be synonymous to using an individual tokenizer for each domain, which actually in real sense is not generalizable. What happens when you have 20 domains, or what happens when you have 20 language scripts? So that's not very feasible. What we did in our work was to make a couple of changes. One was to drop all the like domain-specific boundary predictor, and we used only like a single boundary predictor. And our goal is, because previous work is trying to optimize to, let's say, an alpha value, and alpha here is going to be a compression. You could think about the inverse of alpha as the compression rate. So that's going to be 1 over 0.33, which is going to give you like 3. So here, alphas are the target compression rates. That's what's happening here. What our work is trying to do is to try to say, okay, because we really do not know the ideal compression rate, we want to compress for a random sequence. we want to estimate the compression rate and allow the model to determine how to tokenize the sequence by itself. So what we really want to do is to say, given a sequence length of 100, the model should put boundaries where it thinks boundaries should be at, and the model should do that by itself without penalizing the model if it makes too much, if it goes off a target compression rate. So that would imply that you want to relax the tokenization boundary predictor loss in such a way that you do not penalize the model if it gives you slightly above, slightly below a certain compression rate. So what we're trying to do in the next couple of equations that I will show, largely what those equations just do is to say, hey, giving alpha and beta value, if the number of tokens produced for giving a sequence length falls within this particular value, your loss should be 0, and then you don't get any penalty, basically. So that's what this looks like intuitively. For the equations, this is technically what we're doing. We're trying to replace the binomial loss, particularly, with a simpler loss in such a way that, given we know that K is the target compression rate I want to achieve, and N is the number of tokens I want to get. What I want to do is to say, let's say, for example, the sequence length again is 100 and my target compression rate is 0, but my target compression rate is let's say 33. When you do 33 divided by 100, it gives you the exact value of target compression rate you want to go to. So particularly what we're trying to do is to bound the compression rates to be between alpha and beta. So this is on the right here, you have alpha, and this on the left here, you have a beta. So we're taking the maximum of K over N minus alpha. So K over N here is going to be the predicted compression rate, and then alpha is going to be the specified compression rate that we want to go to. So if this is very minimal, the value is going to be 0. And then if this is 0, so now this could go to negative, which is why we're taking the maximum now. The maximum is going to be 0 here. And then literally that's the same thing happening on the right. But it's that we're just putting 2 bounds basically. And then this is what beta looks like. Beta is just we create a small offset and multiply that with a weighting factor, and that gives you 2 boundaries. Basically, that's what this loss does. And again, the equations are the annotations are quite similar from the previous one, but now we're not just using a relaxed loss, we're also using a single boundary predictor, which eliminates the whole issue of trying to get different tokenizers for different script or different domains. And largely what we're trying to do is to tell the model, see, just do your thing. We won't penalize you if you go up or down. Just try to get the best loss, get the best tokenization pattern you think is optimal for your downstream performance. And largely, how you determine beta and alpha is something that we pre-computed from a data set. I think we highlighted a lot more of how we did this in the paper, but to be specific about it, so in case anyone has more questions, please feel free to ask. I'm going to answer the question. So, but basically, so go back to the previous slide, what we want to do is, okay, so come here, what we want to do is to compute beta and alpha, and then give a loss of 0 in between. And alpha is a value which is defined as given the estimated number of tokens to get in English or a particular language. Beta is just an offset that you get, beta is just an offset, you get by multiplying by a factor here. I want to talk more about how you get that, which is why I'm going back to the previous slide. So because alpha is something that we need to know, so given we want to given a sequence length of 100, we want to compress 3 times. Now that defines what you want to that defines the target compression rate. So alpha is something we should know beforehand while you're training the model. And we computed that by just taking the average of parallel sequences in bytes, and then the sigma now becomes the standard deviation of the average. So you can think about it now. If I have two languages, let's say English and Spanish, because I want the tokens at the end of the day, I want to give the same compression rate for the both of them. What you do is to take the average of the tokens of the sequence or sentences you have in English and bytes. You convert that to bytes, you take your average and you take the standard deviation of that data sets that you have, and then you use that as an offset to determine how much the tokenization should go far, should go above or beyond. Particularly, we have Flexi-Tokens 10x, which is 10x compression rates, and Flexi-Tokens 5x compression rates, and 3x compression rates. So these are basically numbers that we pre-computed using parallel couples, and then sigma here is the standard deviation of doing this. So when you have all of this value, next you would do is to like use that to train a model and see what the downstream performance look like. And we train a model with like 2.6 billion tokens on multiple languages. So we trained on 6 languages, all with 3 different scripts, which is like the Latin script. Spanish and English has a Latin script. Russian and Ukrainian has a Cyrillic script. Hindi and Telugu both have different scripts. And we like brought data set from 5.1, 5.2. And this is the data set distribution on the right. So we trained most of our models we used the 119, that should actually be 119. So we used the 119 parameter model. And then we did the final experiment using the 1B model to show that that's scalable. We can't do experiment on a very large scale because we are training on byte. And I mean, you need a lot of compute to be able to like base off all your experiments based off on the 1B model. So because the HNet, the hierarchical model, I'm trying to use hierarchical to try to make sure, like, let you guys know that the method is quite generalizable. So because the model, again, is divided into multiple parts, again, to describe what's happening here is that you have a couple of transformer layers that give you a representation that you feed into a hidden state, into a boundary predictor. That boundary predictor gives you the tokens that you now feed into the actual language model. So at the top, you have the tokenization module. How we design our model is to use just 2 transformer layers for that. And then the actual LM model, we use 12 layers for that. And then we use like 2 layers for upsampling. For our 1B model, we used up just 24 layers for that. Basically, that's what that looks like. And so when you look at our pre-training results, the 2 major goals we are trying to achieve is that we want tokenization to change after it adapts to a new domain. And we want the performance, we want to get a better performance. And largely, at the end of the day, how you compare tokenizers across different models is with BPC, bits per byte or bits per character. So, but we're using bit per byte actually. So what you see is that the compression rates, the BPC relatively remains the same, while the compression rate of the model goes higher. And now that would mean that when your compression rate is higher, you have a model that runs faster because you have lesser number of tokens. And then with lesser number of tokens, your model is more efficient, basically. So that's basically what our results is showing here. You can look across it, the results remain consistent across multiple languages.
Wait, Abraham, maybe I missed it, but what's the difference between bits per character and compression? I sort of thought I thought of these as almost the same thing.
So bits per character, actually since we use bytes, so this is bits per byte. Bits per byte or bit per character, the metric is basically if you're on a byte level, the metric will simply be the equivalent of perplexity. So that would be you take the loss and you take the exponential of that. If you're on a character level, or maybe you want to do like if you're on a BPE tokenizer level, you would actually take the loss of that and then you take the exponential. I think you divide by the exponential of that and the length of tokens you produce. So what you're trying to do is to remove the factor of variable sequence length across multiple tokenizers. So that's what people use to compare tokenizers with different vocabulary size.
That makes sense. But to me, that feels the same as compression rate, or like maybe a constant factor off.
Compression for us, so no, compression, that would be the same as compression rates. Compression rates for us now is more like, at the end of the day, I give you 100 tokens. How many I give you a sequence length of 100. How many tokens do you give me at the end of the day? So that would be how much you reduce the sequence length to. So you could get 100, you could get a sequence length of 100, and at the end of the day, the number of tokens that goes into the language modeling blocks becomes, let's say, 33. So that's what it is. So they are actually different. They're completely different. So you could think about this as perplexity, and the what's on the right now becomes the number of tokens that you produce. Does that make sense?
Yeah, I think so.
Is it fair to say that what the point of the compression ratio is, that the compression ratio is a comparison to the status quo tokenizers, whereas this bits per character is more invariant of the status quo tokenizers?
Exactly, something like that. But bits per character is relatively is based off the loss, and compression rate is based off the tokenizer, basically. So that's how you can think about it. This is evaluating tokenizer, while the other one is evaluating downstream performance.
Thank you.
Awesome. So what we also see is that we achieve high variance. So when you take the variance of how much compression rates you get, we also see we have higher variance in our models. Generally, if you look at it particularly in the 1B model, so you'd see like there's a lot of high variance here, and there's also a lot of high variance for the 1B models. I'm going to share more results on downstream performance, and then you see what that looks like. So why we have higher compression rates, we also should be comparing with BPE, which is generally what everyone uses. And the problem I had shared previously, where you have like times to the number of characters, in the sequence, because it's completely, eliminated in our method here. Particularly what you see is that and Flexi-Tokens on the right, the plot you have on the right here is that you have the BPE model, the equation from the previous work, which tokenizes to a fixed tokenization number of tokens, and then lastly, which is our new method, which is Flexi-Tokens. And then you see that a tokenization stays the same irrespective of the language or the language script. Whereas in the BPE, if you move on to like other unseen domain or new domain that tokenizer wasn't trained on, you see that tokenization number of tokens is skyrockets to like 128, which is one thing our method achieves, and which is something that we like, which is something that we wanted to optimize for. So now another thing we looked at was downstream performance. And largely we were trying to see, okay, so since we use small model, you pre-train, you also need to adapt on the downstream performance. And then when you adapt to a new domain, adaptation now would mean fine-tuning. You'd see that our model continuously outperforms BPE and the previous baseline that we compared with. This is mostly because our loss is incentivizing the model to say, figure out the tokenization boundary that you think is best for you, like that makes you understand the model well, which is the intuition we had for the model. And then of course our 1B model, we're currently trying to scale the other experiments, but when we try to scale up to 1B, we see that the results also scales like very well. And largely what we have here is Flexi-Tokens 1, Flexi-Tokens 2, and Flexi-Token with lambda 1, 2, and 3. That's basically saying how much allowance do you allow in the loss, which I presented before. And that's just basically what that is. If you compare this, you see that our method consistently outperforms both BPE and like this, and the binomial baseline. Again, we are trying to the major things that we're trying to achieve is we want the tokenization to adapt, and we want compression rate so either stay the same or go higher. And then when you look at the compression rate of these same results, you see that the binomial baseline has the same compression rates after adaptation, but for us, our compression rate goes higher after adapting, while we also get a very good performance. The implication of that is that with lesser tokens, you're going to get charged less, like I shared before. You get better representations because the tokens are now longer. That's what it implies. And the tokens are now longer, and then you get better downstream performance. So for compression rates, the next couple of slides eliminate I'm not going to be talking about. I didn't add that to the slide. That's compression rate. So, but it's in our paper, and what we generally see across all our adaptation is that compression rates continue to adapt when you go to a different domain. I think the result stays consistent again for XNLI, which is a benchmarking data set used, which is like language inference data sets. Again, our method continuously outperforms the BPE baseline and the binomial baseline. Again, if you scale to 1B experiments, you also see consistent improvements when you scale that. So we're not comparing the 1B with like the binomial baseline, but the aim of our 1B experiment was initially to show that what happens when you scale this method completely. So when you go into Sieb seems to be doing way better. And we were trying to see what's happening here, and largely we jumped on the fact that the Sieb data sets, when you do, they just had like 700 training samples in there. And that would mean that if you don't have a very strong signal, the model is not going to be able to learn anything effective, which is basically what we found there, because we only had 700 training samples on the Sieb data set. And then when you also move on to other data sets where we're trying to see, so we also try to adapt to like a medical benchmark data sets. We also try to adapt to data sets with ironies, like an irony detection data set with emojis inside of it, code switching and language identification. And again, our method still performs a lot of them aside for code switching. When you also move on to a generative task, we try to evaluate on translation, and particularly we still see the same pattern where Flexi-Tokens outperforms all other baseline. Keep in mind that all of these results that I've shared so far, the compression rate continues to like evolve as you change the domain of the data set. Again, we did some ablation studies, and what we found was, although compression rate is very great, but compression rate kind of hits a limit. So that would mean if your tokens become too long when you compress to, sorry, excuse me. When you compress like 10 times the actual sequence length, you start losing a lot of performance and the model starts to degrade. So though compression rate higher is better, to an extent, that it's not always true, which is what our ablation studies was trying to find out here. So we could talk more about that later. Another experiment we were trying to look at was what happens, which of the models should be scaled, because we're trying to like look at how we want to scale this stuff moving forward. And we found out generally that scaling the middle model, so again, you have a tokenization model, you have a language modeling model, and then lastly, you have an upsampling model. So you can think about that as an encoder, a language model, and a decoder. And we're trying to look at which one scales best. And lastly, we found that scaling everything is okay. Scaling any part of the model also performs really well. But if you scale the language modeling part of the model, you get a lot more performance overall. So if you have a fixed compute budget and then you're thinking of which part of the model to scale, the middle is good. We're also looking at semantic. We're also looking at like some semantic analysis of what's particularly happening with our tokenization pattern. And then here we were trying to adapt to a completely unseen domain for all of the models. So we picked a BPE tokenizer that wasn't trained on this particular language. We also used our model which was not trained on this language, and we're trying to see how much tokens do you give me? Again, the problem with over-fragmentation comes in with BPE. This text is saying 39-year-old SpongeBob was diagnosed with hypertrophic cardiomyopathy by, which is similar to the text I shared initially. And then what you see here is that the BPE model still gives you 107 tokens, which is really not good. Yeah, this is very not readable because what happens in BPE is that when the tokens are not in the tokenizer, it falls back to bytes. And then when it's falling back to bytes, you have over-segmentation, which is literally what happened in the first slides where you had like too many tokens. Again, that cannot be readable, but I tried to put that here in the best way I could. But you have 107 tokens there. And then when you move on to look at like binomial, you have like 21 tokens, and our method also gives you 17 tokens. When you translate this to English, what you again see is that you start getting like words that make more sense together, like they come together to make more sense. And you start saying things like hypertrophy. Hyper in the word hypertrophy becomes a single word. Cardio in the medical space should be tokenized as one word, but the BPE tokenizer actually separated cardio because the model again has no sentence like cardio. So again, this is not something we want BPE to be doing, but our method is able to like be able to address this particularly. So when you move on to English, that's a completely unseen language, and we use that as an OOD distribution to test our model. Now, when you move on to English to see what's particularly happening, we observe that there's really no trade-off with English because again, the model adapts fine, and pneumonia and a couple of others seems to be coming together to form a token. Again, keep in mind that the model is a byte-level model, and we're trying to like form tokens. We're trying to make tokenization learnable end-to-end and adapt as you change domains. And I think also we moved on to see what's happening in a completely wet domain. Particularly, we were trying to see the issue of what happens when you give very out of distribution tokens that are not so common in the pre-training corpus. And if you followed Kapati on Twitter for some time, there's been this thread that some weird tokens break the models, and then the model completely fails. And then here, the task here is an irony classification task. And in the task, what's happening is you have a text. The text is an irony, and you want to classify if it's an irony or not. And inside of the text, you also have some emojis inside of it. And the English here says, "Oh no, another surprise bonus at work." Just what I didn't need. So that's contrasting. And then you have some extra emojis inside of it. And then when you throw this inside the BPE model, inside the BPE tokenizer, you get 83 tokens. Now that's because what happens again is that in BPE, you give a sequence, the sequence all gets converted to bytes, and then the bytes get merged together to form tokens using the vocabulary of the tokenizer. But when you do not have this inside the tokenizer, like this is what happens particularly. But for our model, the model actually understands that, oh, this multi-byte token are supposed to be one word, and then you can see that the boundaries that fall inside of the tokenizer actually the model groups all of these tokens to become a single token, which is basically what we want, because the model understands that, yes, this all tokenizing it this way makes more sense semantically than like doing it separately. So I think finishing early, basically what we try to do in our work is to address the problem that current tokenization methods are not flexible as a change domain. Like I've shown in the past, what particularly happens is if you train a BPE tokenizer and in your pre-training corpus, generally that's what's currently done, it stays the same. And when you move on to a new domain, like a legal domain or a medical domain or some other domain, tokenization stays the same. And that leads to suboptimal performance in some cases. What we'll find is that when you allow the model to find its best tokenization pattern, which is not fixed like BPE, you get some sort of better results. Also, learnable tokenization or flexible with Flexi-Tokens make tokenization fair across languages. Now that addresses the problem that I shared in the first slide where we had too many tokens for Punjabi. And also with fewer number of tokens, you get increased speed, and with increased speed, things become cheaper for serving the language model. And then future direction that we're looking at right now is to particularly scale the model to all other baselines and also other methods. So that's really the highlight of our work. And I think I can take questions now.
Can you go back to the emoji example?
Okay.
So is this the problem here that when the emojis are converted to bytes and then tokenized, they're just way longer?
So yeah, you're talking about the problem, right? So what happens is
What is that? Those
in-
characters of represent of the emojis, the BPE.
so the BPE are the byte representation of the emojis themselves.
Yeah.
So what really happens is you get 82 tokens. So each of these characters you see is something I try to decode. So these are actually bytes, but I try to sort of decode them to be renderable in the paper. So that's basically what happened. Does that make sense?
Yeah, well, I'm surprised because I would assume a lot of emojis in the data set, and by now they should be tokenized very efficiently, but this is so not the case.
Yeah, so again, this is largely dependent on our training distribution. We trained on FineWeb 2 and FineWeb, which is so we trained on a subset of those. Hopefully we did not see a lot of emojis in our tokenizer, and because there aren't a lot of emojis in our tokenizer training, this is what you get.
Interesting. We're opening up for questions. Feel free to speak up.
I'm really interested in this issue of language. So one of the things that I did to sort of understand what LLMs do is I taught myself to speak Greek using largely ChatGPT. And I'm now doing like in-person, like, Greek, instruction at a local class. So if you take the word on your first slide, cardiomyopathy, that's 4 OpenAI tokens in English. But if you take the same word in Greek where we take the stems from, it's 8 tokens, OpenAI tokens. And that's super terrible. So if we look at how humans do this, like the Unicode Consortium, that's all created in terms of the writing system, right? But we, as humans, we make dictionaries is one of the things that we do with languages. Have you explored use of dictionaries, like maybe as a preferential data set or as some other kind of thing? Because that is a rich source of information for trying to figure out, like, if you had 32-bit tokens, do we have enough tokens for all the words in all the languages in the world? Like, I don't know, when we have enough for characters, right? But like, like when would we run out of tokens for words, and what would you have to mean by a word to fit it in that space? Things like that. Like, it seems like just reading corpora off the web indiscriminately might not be nearly so good as like specifically looking for dictionaries. And there's like Wiktionary is a really great, multilingual resource where you can not only read dictionaries for multiple words, but look at the definitions in multiple languages. I'm wondering if you've thought about using resources like that.
So there's been work that's used like dictionaries, but again, the problem becomes what we're trying to eliminate in such a way that what happens when you move on to a new domain that you don't have a dictionary for, which is kind of what we evaluated. If you look at this result here, so here, this is Udu. We actually did not pre-train the model on Udu, and we really do not know anything about Udu. We just picked the pre-trained model and say, hey, I'm adapting you to this new language, figure out the tokenization for yourself. If you move into the dictionary space, that would mean you always have to know a lot about the language before you can do anything in that space, which is now.
I guess that's kind of like over this. that's one way you could, that's an extreme way that you could do it. But I mean, I guess I would think of it as like there's a holdout process, right? So you could take some things you have dictionaries for and some things you don't. You could hold out the things that you do have dictionaries for, but you want to keep blind, right? And then you could train on the set of things that you didn't hold out, and then you could use the dictionaries that you held out as a validation set, right?
Yeah, that's for a testing set, right? So I'm talking about how you deploy the model on the wild. Like you will always hit that block. Does that like
I'm
make sense?
I'm not seeing
So,
like how is that different?
so
Like,
in the you can so now that could be an evaluation for your model offline.
Right.
But when you go into production, you usually have a lot of usually have a lot of OOD words that would never be in your vocabulary.
for sure, yeah, yeah.
And so the probability of your model crashing is like higher, even if in the test case, it seems like, oh, the model's performance is good. You can never capture your dictionary can never be robust to like what's actually happening outside it.
Yeah. Of course, yeah. So,
Yeah, so
okay. Maybe we should take this offline. It seems like there's two different things that we're talking about, and I don't really understand how to separate them off the top of my head.
okay, that's fine. I'm happy to talk more about it later. I mean, so people have used a lot of dictionaries and code books. But again, the issues with code books and dictionaries is that your model's performance is one as good as the code book or the dictionary. And if you have a bad code book, then at the end of the day, you're only confined to your performance can only be confined to the code book or the dictionary you're using. So what else? Okay, trying to look at what's in the charts. I'm not sure if there are questions in the chart. Okay, so there are no questions in the chart.
There's the one about Chinese or other CJK.
I didn't get there.
Yeah.
Oh, okay. So how should you guys consider Chinese or other CJK? Do you find interesting changing to bits back? As compare with English. So we didn't compare to Chinese and the general CJK languages, but the assumption here is that since everything is gradient based, our methods they applies, which is you convert everything to bytes, and then from bytes you tell the model to compress it as it sees fit. Sorry, probably I think future work are gonna look into considering how tokenization evolves in that domain also. But again, one of the issues with going into languages like that is you also need someone that can help you interpret what your findings are when you look at the tokenization pattern. Yeah, but thank you for the question.
Surely within this community, there might be somebody that you can like partner with to like explore this, and maybe they can like, help you out and stuff.
Sure. Thank you so much. I think we'll look into that also. But so another question saying, is it comparable? Is this work on Hugging Face? So the work is on Hugging Face, but again, our models are not production kind of models. So I mean, there's no point putting that checkpoints on Hugging Face. Any other question?
Yeah, I was gonna ask a small question. Like, so first of all, I'm not an expert on anything. So, like, like considering that large companies like Google and like probably Meta are working on very large like byte-level tokenizers for all their pipelines, like like with Llama and stuff. Like they probably pre-train these models on like trillions of tokens. Whereas in your presentation, you said you process like billions of tokens. So my question is, do you have comparable performance with industrial level like models, or do you think there is a large gap between you guys with the small pre-training tokens and the large company?
I think so which is one reason why we tried scaling to 1B. But we are currently like scaling the baseline model, but I mean it keeps crashing, and the whole school cluster and everything is making the work stay on the queue for like a lot of days, because one scaling up to 1B takes roughly 2.5 weeks. And that's 2.5 weeks on 4 GPUs, and that's something that is not very easy to do. But be comparing to like models like that, it is the only way to compare to that kind of model is to train models at that scale. And right now, I don't think it's possible to train at that scale, which is why we're doing like small models. Hopefully, if anyone picks this, I think so looking at a more recent paper that came out after a paper, which is the HNI paper that trended on Twitter for a while, they have like tons and tons of GPUs, and they only trained, I think, 1.6 billion parameter model. So there's always going to be this disparity if you're doing like open source research.
Thank you.
My God.
It's like it feels like we're fighting like David versus Goliath. You know, I don't know if that even makes sense.
Well, I mean, that makes sense, but that's if you think about it as a fight. What I think is where I think academic research still comes into place, where you're doing small scale experiments in such a way that the insights you can pick from that can be transferable to train larger models that are going to be used in the industry. So it's more like a partnership, if you think about it that way.
Thanks.
Yeah. Any other question? I think I should take this out. So that be all.
Yeah, sounds like that'll be it.
Okay.
Thank
Thanks
you.
everyone for the question.
Yeah, we'd love to hear about any follow-up work after this.
Thank you.
Cool. Thank you. Thank you, everyone.
Bye,
Bye.
everyone.
Thanks. See ya.
Okay, see ya. Bye.